Ladies and gentlemen, welcome to my presentation. My name is Zarbakhsh. I am a professor of simulation and computational engineering at Carinthia University of Applied Science in Villach in Austria. This work is a collaboration of our university with a partner company, Samstec, which is an engineering consulting firm in the area of mechatronics and technical physics. In this presentation, I'm going to tell you about the challenges many research and development groups are facing, that is the design optimization. In this respect, the rapid prototyping, of course, is a great tool for testing new design. However, the finite element, of course, stays as a very versatile tool for optimization and virtual experimenting of the systems. As a case study, I'm going to show you steps of simulation of a RepRap 3D printer, and I will tell you which kind of result you can expect from such simulations. Also, I will tell you about the pros and cons and the difficulties of simulations, and also the difficulties you might have when you are building a simulation group. And finally, I'll present our collaboration offers. A quick introduction about us. We are located in Villach. That's a city in south of Austria in Central Europe, of course, you know. So next time when you visit us, within a few hundreds of kilometers, you can reach Munich in Germany, Venice in Italy, or just Vienna or Salzburg in Austria. I start the main part of my presentation with some statistical data. According to our research, about 1 million people worldwide use computers. 100 million have the knowledge of two-dimensional computer-aided design software or some vector graphic software. 10 million have experience with the three-dimensional CAD software. 100,000 3D printers already sold worldwide. 10,000 are active users of computer-aided analysis, like the finite element analysis software like ANSYS and so on. But only 1,000 people worldwide have potential knowledge to systematically analyze, simulate, and optimize their 3D designs. So it's a challenge for the industry to find experts in these fields. That is exactly our mission. We want to educate people at various levels, CAD, CAE, CAM, and of course we want the people to become expert in these fields. Okay. Now the question is, who is a 3D printing expert and what are the industrial requirements? From our point of view, a 3D printing expert or a university graduate in this field needs to have some knowledge and expertise. This includes knowledge of CAD, knowledge of redesigning ideas into printable parts, knowledge of various 3D printing techniques, materials, available products in the market, knowledge of analyzing and optimizing structural stability. This includes mechanical, structural, and vibrational. And finally, a general quality management, including time, cost, and resource management. Again, these are the requirements which needs to be integrated in a graduate program, and we are looking forward to build joint programs with other consulting firms and universities worldwide to cover more areas. Interestingly, the process steps included in these areas are very similar. The process of 3D printing starts with a model preparation, which is usually done in a CAD software. Next is the material preparation or choosing a proper filament depending on your requirements, of course. Then an important step is slicing, and the next step is the printing process. Finally, post-processing and surface finishing is the last step in this process. Now, if we compare these steps with the process steps of a finite element simulation, we see many similarities. First step of finite element analysis is again model preparation. Next is the material model preparation. This follows with the important steps of meshing, which is equivalent to slicing in 3D printing. Then the computer, of course, should go through a series of mathematical and computational operations to solve the problem. This includes some matrix operation. And finally, we have the post-processing to analyze and demonstrate the result in a proper way. The process of model preparation that I've just mentioned include these steps. Checking the model health, that is to make sure that the parts are seamless, surface normals needs to be checked, and non-manifold geometries should be avoided. These checkings are basically the same in 3D printing and 3D finite element simulations. Next step is the reducing the model complexity. In the 3D printer, the model can be split into several parts. Each part can be hollow, or the parts can be splitted, printed separately, and later glued together. But in the finite element analysis, the extra corner rounding should be excluded to save computer time and, of course, computer memory. And of course, the topic of avoiding the thin walls is the same in 3D printing and finite element simulation. Very thin walls should be avoided. Finally, the goal and learning cycle is quite the same. In both cases, the results are expected to have high stability, lower weight of the parts, and faster process, and of course it means lower cost. And the learning cycle is majorly based on learning from the mistakes, and of course from the previous iterations and experiments. An example of the task which can be demonstrated by the student is the 3D printing of a candle holder, let's say starting from a geometrical shape on the upper left corner of this slide. This geometry includes some overhanging parts which drop during the printing. Of course, in this case I'm talking about the FDM or FFF techniques, and the material is usually PLA or ABS. Now there are two approaches to tackle this problem. The easier approach is to use support material, which is a must if the design is totally fixed. But it has some drawbacks, which I don't want to mention during this presentation. Or we can optimize the geometry by defining a bridge or fillet to make the design printable, so we don't really need a support material. Of course, the 3D printing expert should have the knowledge of both and probably use both techniques depending on the design and requirements. Another example where finite element analysis can help the designer is the simulation of a 3D printer, the mechanical parts of a 3D printer. Our case study in this case is a RepRap Mendel, to be more accurate, RepRap Mendel. Here we have done two finite element analysis in ANSYS, a structural analysis and a modal analysis. The threaded rods are made out of steel and junctions are out of ABS material. The printer is simply located on a table, so the lower areas are frictionlessly supported, and the only structural load in this analysis is the standard Earth gravity. The results that we can expect out of these simulations are deformation, of course the distribution of the deformation, and stress distribution. Of course, each component of the stress distribution can be also the result. In this analysis, we observed a maximum deformation of 0.5 millimeter, mainly because of the extruder's weight. Another result of this simulation is the calculation of the natural frequencies of the system, which is very important, especially when you want to avoid the resonance of the system. Of course, this is a criteria which needs to be considered if you want to go for very fast sprinting, and depending on the feeling patterns, you might consider this frequency. Of course, the simulation result can be different if we change the design, if we change the material, and if we change the boundary conditions of the simulation. So the main advantage and strength of simulation is the ability to answer what if questions. What if we use a different material or setting? What if we change the design, and what are the benefits? How the stability is influenced by the process parameters. How the system behaves in extreme conditions. So these are the what if questions that you may ask. Another question is, what is the scope of the simulation, or what kind of physics can be simulated? So the answer is thermal simulations, mechanical simulations, vibration, fluid dynamic, electromagnetic, which means electrical and magnetic, and many other coupled analysis can also be simulated. This includes 2 or more physics domains. On the other hand, simulation has its challenges as well. The most important thing is that the quality of the analysis depends not only on the quality of the model or the quality of the system, computer, but also on the skills of the modeler. So there's a saying, garbage in, garbage out. Simulation results are sometimes hard to interpret, so supports of the experts are required. And simulation analysis can be very time consuming and expensive, computationally expensive. So sometimes high performance computings are required. And simulation, of course, should not be used when an analytical method or a theoretical approach is already available, because it doesn't make sense to use simulation in such situation. From the management point of view, it's very important to know how simulation can help us. Well, it can help us to do the analysis and studies much faster, which means that if we have a simulation setup ready, then a new design point analysis is just a few steps, and computer can calculate all of the results for you. Another advantage is that the simulation can make the analysis much cheaper, mainly because it's not limited to invest in experiments or other costly items. And you can easily increase the scope of a simulation, which means that the result of one simulation can be easily transferred to another simulation, or into another simulation with higher quality. So if having simulation groups are so useful, why not every research and development film has a simulation group? The answer is because building simulation teams is very challenging. Depending on the type of simulation, you may use a simulation setup which is already available, or you may need to develop a totally new simulation setup. If the simulation setup is already available, then usually you have a set of parameters which represent various design points of your system. In this case, the computer, depending on your parameters, needs to calculate that specific design point, and you only need to visualize and interpret the result. On the other hand, a development cycle is required if your simulation is quite new, and the development cycle includes several additional steps, including model evaluation, calibration, and multiple learning cycles. Depending on your research and development plan, you may decide to only have a what-if cycle in your company or in your group, or you may decide to go larger and have a group for developing new simulation techniques. Usually a what-if cycle covers important and urgent tasks, and you need engineers in this cycle mainly for short-term goals, and usually expect a quick feedback to answer what-if questions. The development cycle on the other hand, usually deals with important but not very urgent tasks. So it means that the scientists who are working here in this cycle, they have some time to investigate the problem. And the project is planned for a longer range, mainly a couple of months up to a few years. So here you need to employ scientists or multi-talent experts, and sometimes you need to hire external consultants. So I conclude my presentation in 2 sentences. 1. Rapid prototyping and finite element simulation have very similar procedure and criteria. 2. Both expertise are needed for professional research and development projects. So these are the major conclusion out of my presentation. And as I promised in the beginning, here is my offer. We offer specialized training and certified programs. We also offer consulting for 3D printing design and simulation and prototyping, and also we offer partnership in project, in consulting, support, and also in funding programs. And finally, if you have any question or inquiries, please feel free to contact us. We'll be very happy to answer the inquiries. Thank you.